I'd like to show you how to use an oscilloscope to make a radio. But before I do that, I want to start with a simple mechanical oscillator. Now, this is a mass that's connected to a spring. The spring, in turn, is being hung from this force sensor. So, if I start the mass oscillating, it goes up and down. Now, the force in the mass is proportional to the rate of change of the mass's velocity. This is usually known as Newton's second law, F equals ma. The force in the spring is proportional to the distance stretched. And that force is being measured by the force sensor. So when we actually measure this force as a function of time, what we see is something that oscillates up and down in sort of a sinusoidal fashion. And this makes perfect sense. We're all familiar with the fact that when you have masses and springs, it bobs up and down, and nothing unusual about that. Well, there's some properties that we know about masses and springs. For example, when we have a small mass, it oscillates quickly, and when we have a large mass, it oscillates slowly. And what I want to show you is the same thing happens electrically. So here we have an inductor. This inductor is a coil of wire. You run a current through it, it creates a magnetic field. And the inductor acts like the electrical equivalent of a mass. That is, the voltage in an inductor is proportional to the rate of change of the current. And the inductor is connected to a capacitor. In a capacitor, the voltage is proportional to the amount of charge. And what we're doing here is we just have an inductor and capacitor, and we're monitoring the voltage by connecting the oscilloscope leads up to the capacitor, just as we have the voltage, we have the force sensor hooked up to the spring, we have a voltage measurement hooked up to our capacitor. And this is what we get. It's an oscillation, it's bobbing up and down. The big difference here is this is bobbing up and down about 600,000 times every second. This is a much faster oscillation. Now, the reason this is bobbing up and down is because we have a signal generator hooked up. Now, the signal generator is actually just hooked up to a resistor. So the signal generator is connected to the resistor. It's not actually connected to this oscillator. It's just connected to this resistor, and yet the oscillator is bobbing up and down. If I turn off the signal generator, so I've now turned off the signal generator, it looks like the signal's completely gone away. But if I turn up the gain, oh, there we go. I turned up the gain on the oscilloscope, and we can see that there's still some oscillation. And furthermore, the oscillation's getting bigger and smaller. So something is causing this oscillator to oscillate. Something's giving it a push. And we can figure out what's giving it a push if we take this light. So we've converted the voltage in the oscillator into, which is electricity. We've converted it to light. I want to convert it back into electricity using this solar cell. So I have a solar cell here. The solar cell's hooked up to a speaker. And I'm going to convert this light that's bouncing up and down. I'm going to have it just turn into a horizontal blip. And there it is. So we have a large oscillation, we get a large amount of light. And we have a small oscillation, we have a small amount of light.
Hit the parking hassle and take a bus from Patty's and Solon right to Kinnick Stadium. The bus departs 4 hours.
And what we have here is we have a radio. So what's happening is that the radio station oscillates at 600,000 times a second, and that they send out a signal, and that causes our oscillator to oscillate. When the radio station wants to send out a loud sound, they send out a very large electromagnetic oscillation, and when they want to send out a soft sound, they send out a small electromagnetic oscillation. And the oscillator oscillates in step with the radio station, and then if we convert that electricity back into sound, then we get loud sounds and soft sounds. And you can actually visually see that when we do this. Well, one of the things you may wonder about this is we just have an inductor and capacitor here. You might wonder, is it possible that if we just hooked a speaker directly to this without any batteries or other electronics, could we actually get sound out of this? And the answer is yes. That's called a crystal radio. And you can look in the internet to find how to make a crystal radio, because it's not too difficult to make inductors and capacitors on your own. And therefore, you can actually make radios that don't require batteries. Another thing you can do is you can use this knowledge of how inductors and capacitors work to actually modify pre-existing radio. You can change the value of the capacitor or the inductor, and suddenly you can get frequency bands you couldn't normally get. So if you take an analog radio, which all analog radios have inductors and capacitors in them, if you take the analog radio and you retune the radio by altering the capacitor or altering the inductor, you can change the frequency. So if you take an AM radio and you have a smaller inductor, well, that will then mean that you can pick up shortwave radio. And if you take an FM radio and modify its frequency range, you can then pick up aircraft communications. So this is how radios work, and you can actually make this system on your own. You can make crystal radios, and if you have an oscilloscope, you can actually see how it works. So that's how this system works, and thank you for watching.